Hello everyone, my name is Kishan Agarwal. Today I'm going to present my TikTok video of design and analysis of algorithm. And my topic is Shuttle algorithm. This is sorting algorithm. So let us begin with sorting algorithm. What are sorting algorithms? So in computer science, sorting algorithm is an algorithm that puts element of list into an order. That is, the most frequently used orders are numerical orders, or we can say lexicographical orders, and either it can be in ascending or descending order. Efficient sorting is important for optimizing the efficiency of the algorithm, such as search and merge algorithms that requires input data to be sorted list. Sorting is also often useful for canonizing data and for producing human readable output. So these sorting algorithms can be classified on the basis of different phenomenons or different parameters. So first of all, computational complexities. So best, worst, and average cases behavior in terms of the size of the list. For typical serial sorting algorithm, good behavior is big O of n log n, with parallel sort in big O of log square n, and bad behavior is big O of n square. Ideal behavior for serial sort is big O of n, but this is not possible in the average case. Optimal parallel sorting is of big O of log n. Next comes the memory usage. In particular, some sorting algorithms are in place, that is strictly memory beyond the terms being sorted. That means no extra memory is used to sort the list of elements. Additional memory is not considered. So that is known as in place algorithm. Next is recursion. Some algorithms are either recursive or non-recursive, while others may be both. For example, merge sort. Stability. Stability or stables algorithm sorting algorithms maintain the relative order of records with equal keys, that is values. Next is whether or not they are comparison sort. A comparison sort examines the data only by comparing two elements with a comparison operator. Next is general method. General methods are insertion, exchange, selection, merging, etc. Exchange sorts include bubble sort and quick sort. Selection sorts include cycle sort and heap sort. Next is whether the algorithm is serial or parallel. The remainder of this discussion almost exclusively concentrates upon the serial algorithms and assumes that the algorithms are serial operations. Next is adaptability. What is adaptability? Whether or not the input affects the running time. Algorithm that takes this into account are known as adaptive. Online. An algorithm such as insertion sort that is online can sort a constant stream of input. So these were the different classifications based on different parameters. Next comes the stability. What is stability? Stable sort algorithm sorts equal elements in same order that they appear in input. For example, in cards sorting example, to write the cards are being sorted by the rank and their suit is being ignored. So this allows the possibility of multiple different correctly sorted versions of the original list. Stable sorting algorithm choose one of these according to the following rule. That is, if two items compare as equal, like the two 5 cards, then their relative order will be preserved. That is, one comes before the other in input, it will come before the other in the output also. In the given figure, you can see that 5 of different designs are in the same order of the input order in the first figure, and the second figure they are in the opposite order. That means first one we can say it as a stable sort, and the second one we can call it as a not a stable sort. In place. What is in place? In place sorting algorithms requires no additional data structure or auxiliary space for the sorting. Examples of in-place sorting algorithms are bubble sort, selection sort, insertion sort, heap sort, quick sort. Not in-place algorithms are which requires additional data, that is auxiliary space is required to sort the algorithm. Best example is merge sort, bucket sort, radix sort. So these are the different types of algorithms based on comparison operator used and the comparison operator not used. So bubble sort, insertion sort, selection sort, quick sort, merge sort, these all are based on the comparison operators, and counting sort, radix sort based, they are not based on the comparison operator. So this was about the introduction to sorting algorithms. Now let us move to our topic, that is shuttle sort. What is shuttle sort? Shuttle sort is an extension of bubble sort. It is used primarily as an education tool. It is same as a bubble sort. What do we do in bubble sort? Bubble sort is a sorting algorithm which sorts the element in either ascending or descending order by popping up out the largest element at the end of the array in each iteration. So let us see what is shuttle sort. It is also known as bidirectional bubble sort or cocktail sort or shaker sort, ripple sort, shuffle sort, shuttle sort, or cocktail sort is an extension of bubble sort. It is used primarily as an educational tool. It tries to mitigate a defect of the bubble sort, the problem of rabbit and turtles. It's a situation when a heavy bubble is placed at the end of the array while the light bubbles that are rabbits are ascending rapidly. The heavy bubbles that are turtles descends only one position per each iteration. This algorithm will speed up the turtle by challenging directions at each iterations. So with each change of direction, the rabbits become turtles and vice versa. It is only allows the larger elements to migrate quickly to the end of the list, but also allows the smaller elements to migrate faster to the beginning. So as we know that shuttle sort is a type of bubble sort. So it also comes under the comparison sort. So what are comparison sort? Just now I said like there are different examples of comparison sorts like quick sort, merge sort, and many other. So in that same order, we have shuttle sort, which is also a comparison sort. So this is the Python code for the shuttle sort. So we have passing unsorted array as vect for this, and we are using two while loops to sort the array. Let us see and understand the code complexity. So this shuttle algorithm, which is also called as shaker algorithm, does not add much to the bubble sort. That means in the worst case, with the data sorted in reverse, the successive runs of the tables require n square minus n by 2 exchanges. For example, for a list of 10 items, it will take 45 comparisons and 45 exchanges as a maximum. That is 10 square minus 10 by 2. Right? The time complexity is therefore quadratic of the order of big O of n square. When the initial order of the items to be sorted is random, it is considered that n square minus 2 star n, that is 2 into n by 4 exchanges will be needed. The complexity will therefore also be big O of n square. So in best case, when the list is already sorted, it will take n minus 1 comparisons with no permutations. The time complexity is linear, that is big O of n. In terms of space used, memory cost of algorithm, the complexity of the shuttle sort is linear. It grows at the same speed as the number of input data, that is big O of n. So When the size of the array to be sorted approaches or exceeds the available primary memory, so that much lower disk or swap space must be employed. The memory usage pattern of a sorting algorithm becomes important, and an algorithm that might have been fairly efficient when the array fit easily in RAM may become impartial. That is, in the scenario, the total number of comparison becomes relatively less important, and the number of times section of memory must be occupied or swapped to and from the disk can be dominate the performance characteristics of an algorithm. Thus, the number of passes and the localization of comparisons can be more important than the raw number of comparisons. Since comparisons of nearby elements to one another happen at system bus speed, which compared to disk speed is virtually instantaneous. For example, popular recursive quicksort algorithm provides quite reasonable performance with adequate RAM due to recursive way that it occupies portion of the array. It becomes much less practical when the array does not fit in the RAM because it may cause a number of slow copy or move operations to and from the disk. In that scenario, another algorithm may be preferable even if it requires more total comparisons. So one way to work around this problem, which works well when complex records are being sorted by a relatively small key field, is to create an index into the array and then sort the index rather than the entire array. A sorted version of the entire array can be produced with one pass reading from the index, but often even that is unnecessary, as having the sorted index adequate. Because the index is much smaller than the entire array, it may fit easily in memory where the entire array would not, effectively eliminating the disk swapping problem. This procedure is also called as tag sort sometimes. And we know that another technique to overcome memory size problem is usually external sorting, in which one of the ways to combine two algorithms in a way that takes advantage of strength of each to improve overall performance. For instance, the array might be subdivided into chunks of size that will fit the array, that is RAM. The contents of each chunk sorted using an efficient algorithm such as quicksort and results merged using a k-way merge sort. This is faster than performing either merge sort or quicksort, as we are using the combination of merge sort and quicksort. So let us discuss the cases of best case, average case, and worst case of our shuttle sort algorithms. So this is the graph shows best case complexity of shuttle sort algorithm. The data size, as the data size increases, number of comparisons also increases. And in best case, we assume that the array is already sorted. So that means swaps are not required. So it forms the best case of our algorithm. Next is average case. That is average complexity of the shuttle sort. Here, as the number of elements in the array increases, the comparisons increases a lot as the swaps also increases. That's why we can see a curve in the graph. That is, the curve is not linear. It is a quadratic curve. That's why the average case complexity of shuttle sort algorithm is big O of n square. Similarly, worst case complexity. Here, the comparison increases more than the average case and the swaps also. So we can say that the curve is more quadratic, but the time complexity remains big O of n square in this case even. Thank you.